Hello everyone, I'm Feline Schieve and I'm going to present the ATMOS paper, A New Sequential Approach to Periodic Vehicle Scheduling and Timetabling, which is joint work with Paul Baumann and Alexander Schieve. So I wanted to start by introducing the sequential planning process in public transport planning, which starts off by designing the infrastructure network consisting of nodes, which are stations or stops, and direct connections between them, which are the edges here. As a first step, a line plan is um, added to this infrastructure network, where lines are to be traveled by one vehicle end to end. For a line plan, a timetable is added here. Lines are considered in both directions, and times have to be assigned to departure and arrivals at stations, and especially the interconnections between different lines at stations have to be scheduled correctly, and minimal and maximal travel and wait times have to be taken into account as well. For a timetable, a vehicle schedule can be found, which is which assigns routes to vehicles such that all the lines are covered, and which exact vehicles are used for this is part of the vehicle rostering problem, and there are a lot more problems which can be added later on, for example, crew scheduling, delay management, and so on. These stages can be divided into strategic, tactical, and operational planning, depending on the time horizon in which they are considered, where strategic is the long-term vision and operational is um, the very short-term planning. We are concerned with the cost-oriented strategic planning, and there the most important question is how many vehicles are needed to operate a given line plan. However, the in-between step of timetabling is more of a tactical problem, and in the strategic phase, not all of the constraints are known, especially the passenger demand, but also some infrastructure restrictions might only be known later on. We are therefore fixing periodic vehicle routes, and for these vehicle routes, we are now determining the minimal number of vehicles needed to cover these routes. In order to evaluate the quality of the strategic vehicle routes, we are also computing periodic timetables and compare the number of vehicles determined in the vehicle scheduling step to the actual number of vehicles needed when a timetable is implemented. This can be interpreted as part of the eigenmodel approach, where the standard um, sequential planning process is changed by reordering the problems. And what we are doing here is we are reordering the vehicle scheduling and the timetabling step by by performing the vehicle scheduling step directly for a given line plan and adding a timetable later on. For determining our vehicle schedules, we are first considering circulations, which will be served by a vehicle end to end. And first of all, for a line plan, we are considering trips, which are the both directions of a line, so a forward trip and a backward trip for each line. And we are adding this to a directed trip graph, where the first station of a trip is connected by an arc to the last station of the trip, and then as it's the directed version, we have both the forward trip and the backward trip for each line. As we are considering periodic vehicle scheduling for a periodic timetable, we assume that the vehicle routes are circulations, which is directed cycles in this trip graph. For such a circulation, we can now determine the minimal number of vehicles needed by dividing the total time of the trip by the length of the planning period and rounding this number up. A vehicle schedule is based on a line plan, now is a covering of all the trips, which is of all the arcs in the directed trip graph. and we are weighting them by the minimal numbers of vehicles needed. Due to this Gaussian operator, an optimal solution to this vehicle scheduling problem is to use an Eulerian tour on all the connected components of the trip graph. However, this leads to a lot of interdependency between the different lines, and therefore it might lead to problems in the timetabling step or even later on in delay management, because then delays would propagate through all of the network. So what we are looking at, instead of solving this for all possible circulations, we are restricting the circulations which we want to be feasible. And therefore, we are considering alpha beta circulations, where alpha is the number of trips and beta the number of unique lines in a circulation. For this circulation here, we have 4 different trips, but only 2 unique lines. A circulation is linked if for each line both directions are contained in the circulation, and then smaller equal beta linked circulations are circulations which contain at most beta unique lines. This concept or restrictions of the circulations was already considered in an ATMOS paper in 2018 by Rolf van Lieshout and Paul Baumann. But what we are now doing is we are adding 2 more kinds of circulations: general circulations, which is circulations which do not have to be linked. First of all, smaller beta circulations, which is general circulations containing at most beta unique lines, and smaller alpha circulations, which are general circulations containing at most alpha trips. We are doing this because in theory, general circulations can lead to needing fewer vehicles, and therefore we are comparing linked smaller than beta circulations containing at most beta unique lines to general smaller than 2 beta circulations, which is circulations containing at most 2 beta trips. And here we see that the optimal number of linked circulations, optimal number of vehicles needed when using only linked circulations can be 3/2 times larger than the optimal number needed in the general case. And this is the case if we have cycles of odd lengths. So if we have, for example, in this case, 5 lines, but we are only allowing linked circulations of up to 3 unique lines. And then in this case, where the length of a trip is exactly t/5, it would be optimal in the general case to use a circulation containing all the forward arcs or all the forward lines and one circulation containing all the backward lines, which would lead to using only 2 vehicles, while when we are using linked circulations, we will need at least 3 vehicles, as we can never get to exactly a total length of a circulation of t. So therefore, it is beneficial to also consider general circulations. As I mentioned before, the number of vehicles computed in the vehicle scheduling step might not actually be attainable when we add the timetable, because what we are adding in this step is our headway constraints and transfer constraints. And here we have an example where we have a infrastructure network with 3 different lines. So one line here, and one line here. And all of these lines are meeting at one station V2, where we have a headway of 15 minutes with a period length of 60. And here we can see that if we allow circulations of at most 2 different trips, we get that we need 3 vehicles in the vehicle scheduling stage and can actually find a timetable such that this solution also needs 3 vehicles in the timetabling stage. However, when we allow circulations of up to 3 vehicles, 3 trips, we find two circulations such that only 2 vehicles are needed, however, which it cannot be extended to a timetable, which needs only 3 vehicles, but we will always need 4 vehicles. The factor by which the number of vehicles increases in the timetabling stage is bounded by t over 2. However, this bound is also sharp, so in the worst case, we can actually get quite a lot more vehicles when we add a timetable. We implemented the models presented here and integrated them into the open software package Lintim, which is developed in Kaiserslautern and is available at lintim.net. We tested our algorithms on 3 different data sets, one small toy data set and 2 data sets, Intercity and Sprinter, from the Intercity and Sprinter network of the Netherlands. What we see here are the line graphs for these 3 instances. We started by computing all the circulations for these networks for our given circulations restriction, and then adding a vehicle schedule and a timetable for evaluation. I wanted to present one example evaluation for the dataset Sprinter and linked circulations above at most better unique lines, and all the other evaluations show very similar results. So first of all, we see that the number of vehicles needed according to the vehicle scheduling stage is decreasing monotonically with increasing beta, which is of course clear because the solution space increases. However, the number of vehicles after the timetabling stage is increasing again because for these solutions later on we are actually using circulations containing more different lines. So we see here that using circulations of containing fewer lines is actually might be beneficial in the timetabling stage. What we also compared this to is the number of vehicles needed when we are using Euler tours, so large circulations, but these give a lower bound of the number of vehicles needed overall. And as we are attaining these lower bounds when we are using circulations of at most 5 lines, and this is attained not only by the vehicle scheduling problem, but also by the timetabling problem, we know that we actually found an optimal solution for a timetable with minimal number of vehicles. To conclude, I wanted to reiterate the most important parts of our paper. So first of all, we introduced a new sequential approach for periodic vehicle scheduling and timetabling. We proposed various methods to restrict the number of circulations and showed that might be beneficial in the timetabling stage. And we evaluated these models experimentally on 3 different instances. We would like to look at speed up techniques for our models, especially by integrating the circulation creation into the model for example, by a column generation approach, as the circulation creation for larger values of beta actually is rather time consuming and especially memory consuming. Another idea would be to pre-process the circulations and to only look at ones which are actually promising for the vehicle scheduling and timetabling stage. And we also would like to include passenger convenience as a second objective to only operational costs. And that's it for today. Thank you very much for your attention.